Hey everyone, welcome to The Explainer. Today, we're going to explore one of the absolute most mind-bending concepts in modern astrophysics. Now, we usually think of light as something that just, travels freely through the vacuum of space, completely undisturbed until it physically smacks into an object. But what if space itself, under exactly the right conditions, could become a kind of cosmic crucible that physically alters the very nature of light? Well, that is exactly what happens when extreme magnetic fields get involved. This brings us to a really fascinating mystery. I want you to imagine the highest energy light in the universe, ultra-high energy photons, just traveling across the cosmos. Now ask yourself, what actually happens when this unstoppable force hits the immovable object of an extreme magnetic field? The answer is incredibly strange and honestly defies our everyday intuition. It doesn't just bounce off and it doesn't just get absorbed. It splits. It multiplies. It fundamentally transforms. Extreme magnetic fields actually act as a catalyst for wild quantum transformations, literally tearing the light apart or causing it to explode into massive showers of completely new particles. No way, right? But it's true. Okay, let's dive right into this. Here's our roadmap for today's explainer. We're going to start by defining this cosmic magnetic crucible, then look at a space mystery called the pulsar death line, and see how photon splitting solves it. After that, we'll bring things much closer to home to see how our own sun's magnetic net creates superpressure shower cascades, and finally, how we're unlocking this invisible universe right here on Earth. Section 1. The Cosmic Magnetic Crucible, the intersection of light and magnetism. To set the stage here, we're looking at the intersection of ultra-high-energy photons and intense magnetic fields. Now, according to the rules of quantum electrodynamics, or QED, the vacuum of space isn't just, empty nothingness. Normally, sure, photons pass right through it completely undisturbed. But when an extreme magnetic field is present, it fundamentally breaks this symmetry. The magnetic field actually polarizes the vacuum itself. It becomes a physical barrier. So high-energy light colliding with this field doesn't just pass through, it interacts directly with the magnetic tension, triggering these totally bizarre quantum effects. Section 2. The pulsar death line, the mystery of the missing radio signals. To see this whole thing in action, let's journey into deep space to look at highly magnetized spinning dead stars known as pulsars. First, we kind of need to understand how they normally shine. It's driven by a process called pair creation. This is where a high-energy gamma-ray photon interacts with a pulsar's magnetic field and physically converts into an electron and a positron. Those new particles then accelerate, emit more photons, and create this massive plasma cascade. This cascading plasma is basically the standard engine that generates these signature radio waves we detect from pulsars down here on Earth. But here's where we hit a massive wall. Astronomers noticed a huge observational gap in their data. When they looked for pulsars with ultra-strong magnetic fields, specifically anything over 10 to the 14th Gauss, they found almost nothing. Classic radio pulsars suddenly go radio quiet, creating what astrophysicists ominously call a death line. The pulsars are still spinning, they definitely have plenty of energy, but the radio signals are simply missing. So where did they go? Section 3. Photon splitting takes over, the quantum scissor. To solve this mystery, astrophysicists Matthew Baring and Alice Harding identified a strange quantum battle taking place. On one side, we have our familiar pair creation, which generates the plasma needed for radio emission. But on the other side, we have magnetic photon splitting. In this bizarre process, a simple high-energy photon just splits into two lower-energy photons. So the crucial point is this: when a photon splits, it loses the energy threshold required to create those electrons and positrons. Photon splitting acts exactly like a quantum scissor that literally starves the pulsar of its plasma cascade, completely choking off the radio emissions. And Baring and Harding calculated exactly when this takes over. The magic number? 4.4 times 10 to the 13th Gauss. Right around this intense magnetic threshold, photon splitting begins to efficiently outcompete pair creation. As Baring and Harding noted in their 2001 paper, this mechanism perfectly explains the radio-quiet magnetars and anomalous X-ray pulsars we observe. The magnetic field becomes so incredibly strong that it actually destroys the light's ability to create matter, forcing it to just split into weaker light instead. The engine stalls out, and the pulsar goes completely dark on our radio telescopes. It's absolutely wild. Section 4. Our sun's magnetic net, the particle multiplier. Let's pivot from these suppressive fields of distant dead stars to a really cool multiplying effect happening right here in our own solar system. Researchers from the Credo collaboration use models to track this. One is a simple dipole model, and the other is a much more complex dipole-quadrupole current sheet, or DQCS model. And this brilliantly illustrates the point. While the complex model is way more realistic for tracking particle trajectories through interplanetary space, both models prove that our sun's magnetic field extends far outward, acting as a giant invisible trap for incoming cosmic light. So what exactly happens when ultra-high energy photons from deep space approach our sun? Well, research by Detail and colleagues proves that the sun acts as a massive magnetic net. For extremely energetic photons, we are talking 100 exa-electron volts here. The magnetic field is strong enough to trigger pair conversion up to 4 solar radii away from the sun's center. That means an incoming photon has a nearly 100% chance of converting into matter well before it ever hits the physical star. To put that into perspective, the effective target area catching these cosmic photons is 15 times larger than the sun itself. Section 5. Super pre-shower cascades, a multiplying chain reaction. Let's walk step by step through the actual chain reaction triggered when a single high-energy photon gets caught in this solar net. It creates a multiplying event known as a super pre-shower, or SPS. Step 1. The ultra-high energy photon hits the transverse solar magnetic field. Step 2. Because the field here isn't quite as suffocating as a magnetar's, pair creation successfully occurs. The photon converts into an electron-positron pair. Step 3. These newly created particles start spiraling through the magnetic field, instantly emitting thousands of secondary photons in a massive burst of light. And finally, Step 4. This huge, exploding cascade of thousands of particles travels millions of miles, a full astronomical unit, right to Earth. Section 6. Unlocking the invisible universe. Catching cascades on Earth. So you're probably wondering, how do we actually observe this bizarre quantum physics raining down on us? Well, when that solar-triggered cascade finally hits Earth's atmosphere, it doesn't look like a normal cosmic ray. Because the particles have been deflected slightly by magnetic fields over that 93 million mile journey, they spread out into this massive, highly elongated, galaxy-shaped footprint. This footprint can literally be millions of kilometers wide across the Earth's orbit. Ground arrays, like those used by the Credo collaboration, are actively hunting for these exact signatures, looking for showers of particles hitting multiple detectors spread out over vast distances at the exact same time. Let's step back for a second and look at how this all builds our overall understanding of magnetic fields and light. This really highlights the incredible thematic arc we've covered today. The exact same trigger, ultra-high energy photons colliding with magnetic fields, causes entirely different results depending on the environment. In the ultra-extreme fields of distant pulsars, photon splitting completely dominates, creating a suppressive deathline that makes the star's radio quiet. But around our sun, pair production dominates, turning a single photon into a massive super-pressure cascade that rains down on our planet. Which leaves us with this final, thrilling thought. We know these super pre-shower footprints are out there, just waiting to be mapped by global detector networks. These high-energy photons might be the byproducts of dark matter annihilation, or maybe echoes of the most violent events in the cosmos. So, if these invisible cascades are raining down on us right now, what new physics will we discover when we finally catch one? Thank you so much for exploring the Cosmic Crucible with me today. Keep looking up and stay curious.